using the tip as a working electrode or as a counter electrode. In both cases, we will generate the OH minus catalyst. But in that case, the ultramicro electrode is negatively charged and the support is positively charged. And in the other case, the support is negatively charged and the ultramicro electrode is negatively charged. And in that case, we observe in both cases the deposition of silica film, but only the ordered film when the substrate is negatively charged. This proves that we need to apply a catalytic potential and to have this pre-assembly of the EMI micelle to get the vertical orientation. So this confirms the mechanism that I proposed you previously. Now that we know that the vertical orientation is in that case, it is not really surprising that the classical Bragg-Ventano XRD characterization did not give any interesting result, and we need to use another technique, which is grazing incidence analysis of XRD. And in that case, indeed, we observe these are exactly the same deposit as previously, the same deposit before and after removal of the aggregates. And in that case, we have the classical spots of the hexagonal deposit vertically aligned. In that case, we have some annealing here, which is due to the worm-like structure of the particles, the ill-defined XRD signal previously observed. And in this case, we have only the signal at z equals 0. So now we can play a little bit with the experimental parameters that are likely to affect the film deposition. And the first one is the concentration of the cetyl-trimethylammonium bromide surfactant template. As you can see here, we can observe the formation of this film in a quite wide CTAB concentration range. And the thickness of the film is not affected by this concentration of CTAB. The concentration must be very close to the critical micellar concentration. On the other hand, by varying the concentration of the tetraethoxysilane, the silica precursor, we observe linear variation between the thickness and these thiols. So knowing the influence of these parameters, we can now define optimal conditions to have aggregate-free films. And in that case, we need to use a rather low tetraethoxysilane concentration, lower than 100 millimolar, and rather short deposition times at the maximum 15 seconds. Otherwise, we have the aggregates. So we have now these well-ordered and oriented mesoporous silica films. Are they useful for applications? And the first characteristic is the size selectivity. If you use a small redox probe like ferrocene, it is likely to diffuse freely inside the mesopore channels, and we have a response which is of the same order of magnitude as on the bare electrode. But if you use a big molecule like hemoglobin, for instance, this molecule is bigger than the pore diameters. Pore diameters is between 2 and 3 nanometers, and in that case, we have a response at the bare electrode, but no response at all at the modified electrode because this cannot cross this film. We can be a little bit more accurate by preparing films of slightly different sizes, 2 nanometers and almost 3 nanometers. And in that case, in using a redox probe, which is a ferrocenyl dendrimer, with the size in between these two values, actually we can make the difference between these two films. For the 2 nanometers pore size films, this probe is not likely to reach the electrode surface, and we don't observe any voltammetric response. When we have a slightly larger pore aperture, 2.9 nanometers inside of 2 nanometers, this dendrimer is likely to cross the film and to give the response, and the critical size is 2.5 nanometers just in between these two systems. So this induces real molecular sieving properties to these films, and we can exploit this in electroanalysis. For instance, I will give you 2 examples. The first example is the detection of the drug propranolol in the presence of hemoglobin. Propranolol is electroactive on a bare electrode, but in the presence of hemoglobin, it loses its electroactivity because hemoglobin adsorbs on the electrode surface. If you use a silica film, the hemoglobin is not likely to adsorb on the electrode surface, and a small propanolol is likely to diffuse through the film and to give a response. Another example is from the Binsu group, directly working on a film with the surfactant template still inside. And this is the example of the detection of chloramphenicol in human whole blood, taking advantage that chloramphenicol is the neutral molecule which is likely to cross to be dissolved actually in the surfactant phase, giving rise to nice voltammetric signals. Whereas the blood interference big molecules are not likely to cross this film, and the ions are also ejected from the surface for hydrophilic reasons. Another example is by attaching DNA on the surface of the film and using a redox probe in solution. The probe is likely to diffuse freely before hybridization. This is here the blue curve. But after hybridization, we observe a current decrease, which is due to the fact that the diffusion of the probe is restricted by this hybridization. And actually, the difference between these two cases is likely to give a calibration curve for the DNA. If increasing the concentration of DNA, we increases the hybridization, and we thus impede the diffusion of the probe to the electrode surface. Okay, so it was size selectivity. And the second property is charge selectivity. If using different kind of redox probes in solution, a positively charged one, two negatively charged one, and a neutral one, respectively before and after removal of the template. Before removal of the template, you have the surfactant phase inside the pores, and you don't observe any signal for the charged species. Only the neutral species, ferrocene dimethanol, is likely to dissolve into the surfactant, and you observe nicely draw voltammogram with a shift towards anodic potential. This is due to the fact that this neutral species is stabilized by the surfactant layer. After removal of the template, all probes are likely to diffuse freely through the film. But we observe significant difference. Only for the positively one and the neutral one, the signals are of the same order of magnitude as on the bare electrode. But when using anions, the signals are much smaller. So how to explain this? We explain this because the silica surface is negatively charged, and this induces some electrostatic repulsion for the anions and some accumulation of the cations. And this effect is even worse when working in a low concentration of supporting electrolyte, 1 millimolar sodium nitrate here for the response of ferrocyanide, which is almost disappeared. And this is due to the fact that in so diluted electrolyte solution, the electrical double layer is much larger than the pore diameters, and so it's impeded the anions to cross this film. We need to increase a bit the supporting electrolyte concentration to start to see a signal, and to increase that much to have a really well-defined signal. Because in so concentrated salt, the electrical double layer, the thickness of the electrical double layer, it becomes smaller than the pore diameter, and it induces free diffusion of all the species. So the anions cannot diffuse freely to this film, except if we work in high ionic strength. We could also think to use a mediator. Here is the response of the ferrocyanide, on a bare electrode. This is the dotted curve. If we use a film electrode, we have the electrostatic repulsion I just tell you about. And now if we had only a small concentration of ferrocene dimethanol, the ferrocene dimethanol is likely to diffuse rapidly to the electrode surface, to oxidize into the ferricinium, and the ferricinium is likely to oxidize the ferrocyanide. So this is a mediated system. So you can play with the ionic strength, you can use the mediator, and the last parameters, you can also play with pH. Here I illustrate the case of a bulky polyanion, which is a polyoxometallate. If you work at pH 4, for instance, the response of the polyoxometallate on the film electrode is much smaller than on the bare electrode because of repulsion, electrostatic repulsion I told you about before. But now, if you work in very acidic medium at pH 0.3, the silica surface became positively charged because of the protonation of the silanol groups. And in that case, even this bulky anion is likely to diffuse through and even to accumulate inside these pores, and the signal is much larger than on the bare electrode. Okay, so if the anions are rejected, the cations can be accumulated. And I give you here the example of the methyl viologen, which is called paraquat. This is an herbicide, a decationic herbicide. And as you can see, using a mesoporous film electrode, we observe a sensitivity which is much larger by almost 2 orders of magnitude with respect to the bare electrode. And this can be exploited for trace analysis. And we use this sensor for detecting the paraquat herbicide directly in the river water, which is the Meuse River in France. And as you can see here, we have a nice response in the nanomolar range with a detection limit, which is much lower than the maximal permissible level. On the bare electrode, we cannot detect it, this methyl viologen alone at all. But this is not so simple, and we have also observed an effect of the ionic strength on the sensitivity, giving rise to an optimal response at 70 millimolar of ionic strength. So how to explain this unexpected behavior? We can understand that at high ionic strength, we can have a competition between the cation of the electrolyte and the cationic analyte. But how to explain the limitation at low ionic strength? And actually, having a look to the variation of the Debye length with the ionic strength, we observe that the optimal value of ionic strength, 70 millimolar, corresponds exactly to a Debye length which is equal to the pore radius. And again, we need to consider that when the methyl viologen will accumulate inside the pores, it is not alone. It is with his counter anion. And in that case, this anion cannot go inside the pores when the supporting electrolyte concentration is too low, because the Debye length is larger than the pore radius, and we have an overlap, total overlap of the electrical double layer. And just to confirm this, we have studied the effect of the pore diameter using surfactant with different length, and in that case, it gives mesoporous films with pore radius increasing from 0.8 to 1 to 1.5 more or less nanometers, and the optimum of the response was obtained for an ionic strength corresponding to a double layer equal to the radius of the pores. So this proves that indeed we need to optimize the ionic strength to get larger pores due to the correspondence between the electrochemical double layer thickness and the pore radius. It is also indirectly a way to measure the ionic strength of a medium. Okay, so as an intermediate conclusion on non-modified films, I hope I convince you that these films made of amorphous silica materials, but well ordered at the nanoscale, we can have some size selectivity, and this can be exploited as for molecular sieving and as protecting layers against biofouling. We also observed charge selectivity due to the fact that the silica walls are negatively charged. This can be exploited for the accumulation of cations, yet with an effect of ionic strength. I just told you about that. And these films are also rejecting anions due to electrostatic repulsion, but it is possible to play a little bit with the ionic strength, to use a mediator, or to play on pH to vary the perm-selective properties of these films. We can also pre-concentrate neutral or hydrophobic species. Okay, all these results obtained with non-modified films. So the next step is, could we be able to modify and to functionalize the internal space of this membrane to enlarge the extent of possible applications? And when we think about functionalization of silica, we think about using an organosilane reagents which can be grafted on the silica or in the porosity of a porous silica material. And this can be used for almost any kind of silica materials, except for these films. When we attempted to graft such organosilane inside the oriented mesoporous silica films, you observe a complete blocking of the system. You have here the response of ruthenium trisbipyridine in black on a bare electrode, in red on the same on a film electrode after removal of the surfactant template, and after grafting, I think it was grafting an aminosilane, we observed a total blocking of the pores. So that means that probably the grafting occurs only at the extreme surface of the film and blocking the pores. This is probably due to the residual water in the system, making some co-condensation of this system in addition to the grafting. We can think about removal of water, which use several treatments to remove water from the medium. But in the best case, we can observe a small perm selectivity, but it's almost impossible to graft without blocking effects due to the fact that the film is a small quantity of solid material in contact to the solution. And even if you have small amounts of water, this gives rise to unwanted hierarchical polymerization. So I need to find another way. And another way could be the co-condensation of tetrahydroxysilane and an organosilane. And co-condensation actually is possible, but it is quite limited. It is restricted to quite simple organosilane, like the aminopropyl groups, and also to a certain extent of these aminopropyl groups in the starting soil. Up to 10% of APTS, we can observe these well-ordered films, but at larger concentration, we observe non-ordered films. Anyway, we can try to apply this amine functionalized films for electroanalytical purposes. And one example is the pre-concentration of copper ions, which are likely to be chelated by the amino ligands. And in that case, we can accumulate this and detect by anodic stripping differential pulse voltammetry. And in that case, the intensity of the response is proportional to the content of amino group inside the film, but just up to 10%. Then for 15% or 20%, even if you have more amino groups in the material, the signal is significantly decreased. And this is due to the fact that these films are no more ordered, as I showed you previously. We can also apply this for trace analysis. And if you compare the response of non-templated films and a templated one, for the analysis of 1 micromolar of copper, you observe an increase of intensity by 1 order of magnitude. And for trace analysis, for example, the analysis of 10⁻8 molar of copper, which yet rather long pre-concentration time, you observe a well-defined signal at the ordered film materials and none almost no signal for the non-templated films. And this confirms the interest of this very well organization and the orientation for fast transport and efficient pre-concentration. Okay, we can also use a simpler organosilane just bearing methyl groups, and in that case we can increase a little bit more the extent of functionalization while keeping the hexagonal order and the pore orientation. Up to 60% of methyl 3-ethoxysilane we can get some well-ordered system. The thickness of the film is decreasing by increasing the amount of organosilane in the material. This is due to the fact that the condensation rate of an organosilane is it's not as fast as the condensation of the tetraethoxysilane. Slower, sorry. In that case, you can keep the organization up to 60%. The problem is that it is only methyl groups and not really useful for applications. The only effect that you can observe is variation of the hydrophilic to hydrophobic balance. I just illustrated this here. This is a response of ruthenium tripyridine or ferrocene ethanol as a function of the extent of functionalization and the number of methyl group in the mesopores. If you increase the methyl group content in the mesopore, you have less and less space for the species to diffuse through the film, and of course you observe a decrease in the sensitivity in both cases when you increase the amount, the extent of functionalization. But as you can see, this decrease is different. If you use a purely hydrophilic probe, you reach the zero value, you block completely the film for the 60% film. But on the other hand, if you use a neutral probe, which is a little bit less hydrophilic, the decrease is a little bit slower, and you have still a well-defined response of this ferrocene ethanol, even at 60% of the film. So you play only with the hydrophobic-hydrophilic balance. So now, if we would like to have more sophisticated organofunctional groups inside the film, we need to develop another methods for functionalization. And what we proposed is a combination of the electro-assisted self-assembly of an azide functionalized film with the click chemistry. So in that case, in addition to the tetraethoxysilane in the starting soil, we use an organosilane bearing some azide group, and after co-condensation, we will expect to have the azide group inside the material. And then this azide group could be exploited in the click chemistry reaction, the Huysgens reaction, with alkene-bearing groups, for example, ferrocene, propargyl ferrocene, and we will see if it works or not. So we have first to check if this co-condensation of tetraethoxysilane and azide propyl trimethoxysilane is likely to give ordered mesostructure. And the answer is yes. We can observe the well-organized film in an hexagonal geometry. All the pores are oriented normal to the support. We can observe this orientation and high degree of ordering by the grazing incidence XRD, and also the film thickness is decreasing somehow by increasing the amount of organosilane in the starting soil. This is due again to what I mentioned previously, the slower condensation rate of an organosilane with respect to the tetraethoxysilane. But most importantly, this high level of ordering and vertical orientation is maintained up to a large amount of organosilane in the material. It's quite surprising, because usually when you do some co-condensation between an organosilane and a tetraethoxysilane, you are limited to 10 to 20%. In that case, we think that the zwitterionic characteristic of the azide groups acts as a stabilizing effect between the negatively charged silica surface and the positively charged surfactant. We can see really the incorporation of the azide through infrared spectroscopy by the typical response of the azide at 2,100 per centimeter, and we are able to incorporate quite a huge amount of azide group, yet a little bit less than the theoretical one expected from the ratio between the azide and the tetraetoxysilane, due to, as I mentioned previously as well, the slower condensation rate. So we have ordered films oriented with azide group inside the material. Now, if we characterize the permeability of this kind of films using ruthenium hexamine in solution, as you can see, before extraction of the template, we don't have any response. That means that the film is perfectly deposited on the surface. And for a film bearing 10% of azide, we observe a well-defined response after removal of this template. So that means that even if the presence of this azide, we have a fast diffusion of the probe in the solution. This diffusion of the probe is slightly decreasing when increasing the amount of azide group in the material, because there are less and less space available for this probe to diffuse through the film. But anyway, even at 40% of functionalization, the film is still porous. So that means that the azide group should be accessible for click chemistry. And this is exactly what we checked using different kinds of alkene-bearing reactants. And I show you here the example of the propargyl ferrocene. And indeed, this ferrocene is likely to be bound by click chemistry inside these very small pore channels. And this is supported by infrared spectroscopy. And once grafted inside these pores, the ferrocene groups were electroactive, as you can see here, well-defined ferrocene to ferrocenium signals, and the intensity of this signal was increasing by increasing the amount of azide group in the material. So that means that we can graft more and more ferrocene group, and these ferrocene group are electroactive. This can be surprising because the silica is non-conductive material. And so that means that the electron transfer mechanism is actually the electron hopping from one ferrocene to another one. And this also explains what at very low amount of ferrocene, lower than 2% of azide group in the material, we did not see any response. Even the ferrocene group are really in the material, they are too far from each other to enable the electron transfer. So the electron transfer mechanism can be studied a little bit in more detail by varying the potential scan rate. And here I compare the results obtained for 10% ferrocene film and much higher loading, 30% of ferrocene. Of course, by increasing the amount of ferrocene, you increase the intensity of the signal. But most importantly, the peak-to-peak separation is much smaller when you have 30% of ferrocene. So that means that the kinetics of the electron transport is much faster in that case, because the ferrocene groups are much closer to each other. Here they are much, the distance between each ferrocene is a little bit much larger. In all cases for potential scan rate larger than 20 millivolt per second, the signal, the peak currents are directly proportional to the square root of the scan rate, indicating that we are limiting by the diffusion. It can be the pseudo diffusion of electron during the electron transfer, but also to the charge compensation. Because each time you oxidize a ferrocene into ferrocenium, you need a charge compensating anion to enter into the film to compensate the charge. And depending on the size of this anion, if you use a small anion, you have a large response because it diffuses fast through the film. But when you use a large anion, like the paratoluene sulfonate, for example, you have significant restriction because you have restriction to diffusion inside these pores. So we need to find a compromise to have an an amount of ferrocene groups large enough to have fast electron transport by electron hopping, but not too large to let the place for the counter ion to enter the material. And having realized that when the ferrocene is oxidized into ferrocenium, an anion must compensate the charge, we can think about using this effect to detect these anions by an amperometric way, but indirectly. And for this, we use a quite special medium. We will work in flow injection analysis mode, but using pure water as an electrolyte, as a solution, as the flow electrolyte. No electrolyte, no added supporting electrolyte, which is not common in electrochemistry. And at some times, we inject a small amount of anion. In that case, it was nitrate. And so we observed a flow injection signal, which has two components. The first one is a capacitive contribution, because when the nitrate sample is contacting the electrode surface, it induces some conductivity, and the potential which is applied is really applied to the electrode. And so you have the capacitive current. And in addition, you have also the Faradic contribution, which is due to the oxidation of ferrocene, which becomes possible due to the presence of the charge compensating anion. When you use only a bare electrode, you have only the capacitive contribution because you don't have this reaction. The problem is that when you inject successively the nitrate, as you can see, the intensity of the signal is decreasing, and it's even worse if using a second wand. And this is due to the fact that we consume the ferrocene group that has progressively oxidized, and we have less and less ferrocene group in the film, so the signal is decreasing. So we regenerate this ferrocene group, and a way to regenerate this is to work not by applying a constant potential, but by applying a square wave amperometry. Again, as we are in pure water, we need to apply a big potential difference, and in that case, we oxidize the ferrocene, we reduce the formed ferrocenium, and in that case, we can observe very reproducible response without any loss of the sensitivity, and the signal is directly proportional to the concentration of this anion. As you can imagine, the selectivity is not good because all anions will give a response, but we can use this after separation of these anions, for example, in ion chromatography. And when using a suppressor, we can observe quite sensitive response. This is here in blue. The cell was not optimized, so it is noisy. But anyway, if you compare with the orange response, which is conductimetry detection, we observe all the peaks, and the response was similar in both cases, yet a little bit more sensitive with the electrode, because in addition to the effect of conductivity, we have also an indirect amperometric response. We could also think to exploit this particular ferrocene functionalized film for the detection of tires. Indeed, when using ferrocene, or ferrocene in solution, for instance, when you oxidize ferrocene into ferrocenium, it's likely to oxidize tires. And this is shown here on the black curve. You have the oxidation of cysteine or glutathione. On the red curve, this is on bare ITO using ferrocene in solution. And on the black curve, it is for the ferrocene functionalized films on ITO. In both cases, the electrocatalytic response is present, but it seems that the film has better response for cysteine than glutathione. And the only difference, in solution, there is no difference. But in the film, there is a difference. And why this difference? Probably because the cysteine is much smaller than the glutathione, and the diffusion inside the film is faster. So we can think about having a selective detection of cysteine over glutathione. And actually, by working in the flow injection analysis, we can see a direct directly proportional response to the cysteine concentration. And if comparing the response of cysteine to the response of glutathione, that indeed we have a very small response for glutathione and bigger one for cysteine, which induces some selectivity in the detection, probably due to confinement effects. So just to end this, I would like to show two slides opening new directions. And one new direction is to get not only one organic function in the material, but two organic functions in the materials. And in that case, we need to co-condensate several silane reagents, the tetraethoxysilane, the isopropyl trimetoxysilane, as I told you previously, for incorporation of a Zy group, and the mercaptopropyl trimetoxysilane to incorporate thiol groups. In that case, we obtain thin film bearing a mixture of thiol and azide. And these two groups are likely to be exploited in two different click reactions. The first one is the classical Huysgant reaction, the copper one catalyzed azide alkyne click reaction. We saw that for incorporating cobalt-osmium group. And then we could also exploit the thiol-in click reaction, which is catalyzed by amine, to incorporate ferrocene group via the reaction of an alcene with the thiol group. And due to the fact that the catalyst is different in both cases, these reactions are really selective. So we can bind one group and then the other one. And just to prove you that it works, these are the response of these two groups that have been incorporated in the material. And this opens the way to functionalize this system with a huge amount of organic material. And the last example is that we could also fill these mesopore channels with coordination polymer. And actually we showed that when using a special kind of a coordination polymer, which is an iron triazole complex, which is formed a coordination polymer, we can use this really as a template and to form the silica network around. And after the formation of the film, this template, which is actually a coordination polymer, is electroactive. And the electroactivity is very nicely defined, and you can use very high potential scan rate, up to 4 volt per second. I just illustrate here from 0.2 to 1.2 volt per second, and this is very stable. So we have a very reversible and very fast electron transfer inside this insulating material. And we could exploit this electrochemical activity of the coordination polymer to detect by electrocatalysis H2O2, for instance. And I just illustrate this by flow injection analysis. You can have a good dynamic response in the micromolar range. Okay, I think it's time to stop here. And I do hope I convince you that using electrochemistry to form highly ordered and vertically oriented mesochannels, we can apply these for interesting electroanalysis applications. So the sol gel electrode generation in the presence of surfactant is likely to give this vertical orientation. These films are characterized by both charge and size selectivity properties, which can be exploited for pre-concentration as permanent selective coatings, or these properties are affected by ionic strength and pH. We can also combine this electro-assisted self-assembly to click chemistry, and in that case, you can get a highly functionalized films that can be applied to a wider range of applications. For example, if using redox moieties inside these materials, even if they are insulating, you can keep the electrochemical activity. You can exploit these for the indirect amperometric detection of non-redox anions, giving rise to direct proportionality between the concentration of these anions and the electrode response. You can detect selectively cysteine over glutathione, and you can have also some electrocatalysis catalytic detection. I just wrote an account explaining all the interests of this approach. Finally, I would like to thank my colleagues and co-workers. First, Grégoire Herzog, who supervised people on the analytical applications, and Neus Fidla, who is a specialist of click chemistry and molecular electrochemistry, so he supervised the functionalization aspects. Then the PhD students and postdoc, Émilie Sibotier, who was the first to see the possibility of electrochemistry to get these films. Aurélie Gou optimized all the parameters to get aggregates-free films, for instance. Yann Guillemin used the local deposition and the functionalization by methyl group. Then Cheryl Carman studied all the modulation of electron transfer of ferrocene by varying the ionic strength. Tokir Nasir exploited the pre-concentration and electroanalysis of cations, for example, the herbicide paraquat. Samuel Haoulou worked on the part I present you on the coordination polymer. Diomila Basnik investigated the mass transport reaction inside the films, and Himanshu, who is from India, actually worked on the selective detection of cysteine. Finally, I thank you for your kind attention. I spoke a little bit fast to reach the time because we lost some time at the beginning. I apologize for the problem at the beginning. I thank you very much, and I thank again the organizer for the kind invitation.
Thank you very much, Professor, for your clear and elegant presentation. And now this session is open for discussion.
Dear Professor. Hello.
Yeah, you are audible.
Very nice presentation, Professor. I have one doubt. You have used paraquat as an analyte or?
Yes, I use paraquat.
Paraquat. You have used paraquat as an analyte, no?
Yeah, better you type your question in chat box. Our chat person will convey to him.
Yes, that would be perfect.
Yeah.
And transmission was not so good. I understood that I used the film for paraquat detection, but I'm not completely sure.
Good morning, sir.
Maybe you write the question in the chat.
Yes, sir. He is typing.
Okay, thank you very much. Sorry. Yeah, paraquat was used as an analyte completely. So paraquat is positively charged, so it could interact with the negatively charged silica surface, and it could accumulate. And actually, not only the charge is likely to affect these accumulation processes, but when you have some aromatic group, which is the case of paraquat, the efficiency of the accumulation is much better. For example, if you accumulate ruthenium hexamine, you have just a small increase in the signal. If you accumulate paraquat or ruthenium trisbupyridine, because of the presence of this aromatic group, we enlarge the pre-concentration effects. And this is thought to be due to not N-pi interactions.
It is a toxic or not toxic?
Oh yes, it is toxic. It is an herbicide, which it was widely used for in the culture of potatoes, for instance. I think it is still used a bit in the US, but it's completely forbidden in Europe for the moment. but it is a contact herbicide. So that means that there is a contact with the green part of the plant and not with the potatoes themselves, for instance. But there are some problems if you drink this herbicide. You have big problem because there is no way to solve. And usually when people drink this, there are some problems in Ireland, for example, in some 10 years ago. And the only way to more or less solve the problem is to give some clays for people to eat. And in that case, you have some absorption of the paraquats. But there is no way to solve the problem from the medicinal point of view. No, this is toxic, yes.
Okay, thank you, sir.
You're welcome.
Any other questions or clarifications?
Good morning, sir. I'm Vasanta.
Yeah.
Yes, madam.
Yes, sir. Sir, actually, it's a very interesting and useful talk for our group. Thank you very much for your interesting talk. Actually, I have some small doubts, sir. During salt gel process, there is an increase in the pH in the interface during the deposition of the film. But sir, are you using any in situ technique to measure the pH increase during the deposition of the salt gel film, sir?
To measure the pH during deposition?
Yeah, in situ. Are you measuring the pH, sir?
We did not measure directly the pH during deposition. It's a good question. What we did is to use a dye, and in that case, we can see the change in color. So we are sure that there is a change of pH, but actually it should be more or less between 10 and 11, around 10, between 9 and 11 to be sure, but we did not measure this accurately. We are sure that it is above 9 for sure, because we use the dye for that, but no clearer ID. Actually, it should depend on the applied potential, because when you
that's right.
You will apply more cathodic potential, you will generate more OH. So we can see this indirectly, but we didn't.
In that case, the film will be affected. No? The film property will change.
Yeah.
Potential and with the pH.
For sure. We can play on two parameters. The potential, which will define the concentration of OH minus, and the time also. Because when you increase the time, you let the polycondensation of the silica accelerate. No, you are completely right. And very recently, some people try to deposit this kind of film using a rotating disc electrode in order to let the OH minus to diffuse a little bit, because you know the diffusion layer is much thicker than the film, and so you form the OH in some tenths of micrometers, and the film is some tenths of nanometers. So there are 3 orders of magnitude difference, and that's a problem, because when you let the time spend longer, you will form particles in this diffusion layer, and these particles will aggregate on the electrode surface.
Sir, actually, initially it is forming the thin film form. During the deposition, initially it is forming a film nature, and then it is forming an aggregation, more aggregation.
Yeah. The thin film is always, sorry.
After deposition, are you removing that aggregation with any aggregation on the surface? How you are doing? Okay, sir. Yeah,
2 ways. If we have the aggregates, we could remove this aggregate simply by a scotch tape. The scotch tape is enough, and the adhesion between the film and the ITO surface is strong enough, and the film is still stable after removal of this aggregate. But the best way to avoid the formation of these aggregates and particles, and this is what I mentioned maybe a little bit rapidly. If you decrease the concentration of tetrahydroxysilane, and if you shorten the deposition time, of course, you have thinner films, but you avoid the formation of the aggregates.
We have to control the time.
Yeah.
Time and potential is very important parameter for this.
As well, you need to optimize the potential depending on the electrode support that you will use, because the over potential of the formation of OH minus is different from one electrode surface to another one. If you would like to avoid the optimization of this applied potential, you can use galvanostatic conditions. And in that case, you applied a current density and not a potential. And if you have density, independently of the electrode nature, you can control the formation of this film without requiring the optimization of the applied potential.
In that case, galvanostatic method is better than potentiostatic, sir?
Yes, you can use potentiostatic, but you need to optimize the potential, or use galvanostatic conditions and you don't need to optimize the potential.
Sir, which one is better, sir? Galvanostatic is better to control the film thickness, or potentiostatic, sir?
I would not say better, but I would say easier, because galvanostatic conditions, you don't need to optimize.
Okay.
So not really better, because you will obtain the same kind of film, but it's easier to avoid controlling the potential. Yeah.
There also we have to optimize the current density, sir. In galvanostatic method,
yes, of course. But you do that only once, only one time, because it's same for all electrodes. Of course, and you are completely right. Huh? We have published this in the Chemistry of Materials paper, and you can have the information about that. Yes, of course, we need to optimize the current density. You are right.
Sir, another question. Actually, you are functionalizing the silica gel to increase the charges on the electrode surface for charge selectivity. In that case, the electron hopping is taking place. That mechanism is through ferrocene. Electron hopping, it's following electron hopping. So it's when you are functionalizing that ferrocene on the electrode surface, it becomes completely electron hopping mechanism, or mixed type of mechanism is followed there, sir, or completely electron hopping also. I want to know that. And
the electron transfer, the mechanism is electron hopping from one ferrocene to another ferrocene group. It's like redox polymer. Like in the redox polymer, but in the redox polymer, you can have some movement between the polymer chains. In that case, in the present case, the silica walls are mechanically stable. And so the groups are really physically linked to these groups, and they cannot move. Just have some flexibility due to the propyl chain. And in that case, the only way to have the response is that one ferrocene is close to the other one, and the electron is hopping from one ferrocene to the other one. This is the first part of the mechanism. The second part is that when you oxidize one ferrocene into ferrocenium, you have the formation of a cation, and you need an anion from the solution to diffuse inside to compensate the charge.
Yeah.
You have both kinetic limitations. One is the kinetic of the electron transfer between the ferrocene group, and the other one is the kinetic associated to the diffusion of inside the material. And depending on the relative density of the ferrocene group, you can shift from one limitation to another one. Few amounts of ferrocene, what is limiting is the electron hopping, because the ferrocene are far from each other. And when you have huge amount of ferrocene, this electron transfer is fast, but you have less and less place for the anion to come inside. And so the diffusion of the counter anion becomes limiting. So there is an interplay between two limitations.
Two limitations. Okay, sir. Okay, sir. Yeah.
Okay, Professor, there is a question from the audience. One of the questions is mesoporous silicon prepared using any electrochemical techniques?
Yeah, as I mentioned previously, we can use the potentiostatic technique by applying potential, but the optimal potential will depend on the nature of the electrode, or we can use galvanostatic conditions, and in that case, we need to optimize the current density, and then you can use any kind of electrode we want. So the only technique is galvanostatic or potentiostatic electrochemical approaches.
Okay.
And then there is another question on use toxic elements like tellurium for electrochemical sensor.
Yes.
In that case, we didn't try tellurium. We tried some electroactive heavy metals like copper or mercury, chromium as well, but not tellurium yet. And then we also applied indirect amperometric detection for anion, non-redox anion detection or electrocatalysis. But other groups start to work also on that kind of mesoporous films. And there are the group of Binsu in China is measuring different kinds of organic compounds, especially drugs, the different kind of drugs, also some explosives. The interest is working in situ because of the anti-biofouling and anti-fouling properties of these films. I didn't see any example for tellurium for the moment.
Okay. Thank you.
Hello. May I ask a question?
Yes, go ahead, please.
Hi, Dr. Valkaris. This is Ritu from IIT Delhi. I have one question. I'm also working with mesoporous silica, but we are making silica nanospheres for drug delivery and other things. But I'm very curious about like if we can add any metal salt like gold chloride or platinum or palladium salt to the precursor material, and when we are doing the electrode deposition, can we see any like a mixture of silica film with some nanoparticle deposited on the surface, or like a gold nanorod forming within the film?
Yes, we tried actually to use these films as a template for deposition of nanomaterials like nanofilaments, for instance. For the metals, it's extremely difficult to get nanowires, metal nanowires in so small pore diameters membrane. And we did not succeed. We sent some of our sample to the group of in Southampton because he is a specialist of electrode deposition, and especially he can work in supercritical fluids. And in that case, you have a huge pressure, and actually he succeeded once to get some thin wires, but that they were not mechanically stable.
Okay.
And if we cannot do that for metals, we can do for conducting polymers, synthetic metals, I mean. And it's possible, for example, to electrogenerate polyaniline nanofilaments, individual nanofilaments of polyaniline in each pore. And the behavior of these wires is interesting because all these wires are separated from each other. There is no cross-talking between these wires. And so the reversibility of the electrochemistry of polyaniline is much better in that case. And these nanowires exhibit some electrochromic properties. And the only problem is if we want to remove the silica after, we need to ensure a good covalent bond between these nanofilaments and the electrode support. And we just method on that by combining this by electrocrusting the bottom of the pores and then forming the polyaniline by electropolymerization.
No, actually, I was thinking is if we don't want to remove the silica, we want silica film as well as the gold nanowire. It will help in like act as a anti-biofouling agent. Like the pores will be present for better electron transfer, plus gold will be there to increase the sensitivity. So that way, I was thinking like it would be good if we can try something like that, and if we can achieve like
Yeah.
porous material with embedded with some metal nanoparticle to increase the sensor properties.
Yes, for sure. You could reduce metal ions, and in that case, you can have nanoparticles, but maybe not wires, at least in so small pore diameters. I don't know what are the pore diameters of the film that you use. Maybe they are a little bit larger.
No, actually, what I'm doing is we are preparing silica nanospheres, not films. So when I listened to your talk, it was very interesting. Like we can prepare the film. So I was thinking the pore size was 10 to 15 nanometer in my spheres. We are using C-tab as a surfactant to preparing the pores in that.
Okay, thank you, Ritu. Yeah. Okay, in the absence of further questions, we thank Professor Valkaris for his excellent presentation. And on behalf of the organizing committee, we thank you very much, Professor, for your time and your nice talk. And I hope the audience have really enjoyed his presentation. Thank you very much, Professor, for your valuable time.
It was a pleasure to be with you. Thank you again. Thank you very much.
Thank you very much for your have a nice presentation. Thank you, sir.
Thank you.
Thank you. Thank you.
Thank you, sir. It's really, it's true statement because our eyeballs are not moving for 1 hour with your slides. It's really fantastic. To be very honest, your lecture is very detailed, informative in all your research parts, what you have touched. In our mother tongue Tamil, one proverb is there. I don't know whether you can follow that one. Oru paanai sotrukku oru soru padam. What does it mean by in English? One piece of single rice is enough to test the overall quality of the food in the pot. So your work is just like that. Your jump piece of work is example for this kind of thing. Once again, we young researchers are very blessed because I just saw your name in editorial member. In my life, I never expect to meet you through this kind of virtual meet. For this, on behalf of organizing team as well as ma'am, I would like to register our sincere thanks to you, sir, with us. Thank you so much. Jehovah mercy, sir.
Thank you.
Thank you. Thank you very much.
Sir, thank you, sir.
Thank you.
In this connection, I would like to acknowledge our chairperson as well as our own family member, Professor A. Dakshinamurthy sir, for spending his valuable time with us, and also the chair in this wonderful day in a very effective manner. Thank you so much, sir.
Thank you very much.
Yeah. So a kind announcement to the participant. We have completed the oral and the postal session in yesterday itself. But even though some of you have requested to give one more session, actually we planned for today, but unfortunately we have completed. Suppose if you would like to give your oral or postal, yes sir.
I think Professor Valkaris can leave, no?
Yes, sir.
Professor, you can just sign off. Thank you very much. Thanks a lot. Thanks a lot for your time. Thank you.
Thank you, sir.
Yeah.
Yeah. So continue with that. Some of them have requested to give one more chance. If you wish, you can participate, and we will intimate the session soon. And hereafter, we have on electrochemical instrumentation virtual live demo from Norway. I think Mohammed Aftab with us. We will shortly join by 11:30 a.m. Mohammed Aftab, are you there? Mohammed?
Yes, hello.
Yeah.
Hi, good morning.
Yeah, very good morning.
Yeah. So Dr. Martin Peacock from Zimmer and Peacock will join at 11:30, and then we will continue with the demo onwards from 12 to 1 p.m.
Yeah. Thank you. Our convener, ma'am, is there. Ma'am?
Sir, actually, good morning, sir. Mohammed. Sir, very good morning.
Good morning, ma'am.
Sir, actually, I have another important meeting during that time.
Okay.
Sir, you can proceed, but I will join after finishing my meeting, sir. Sorry for...
Okay, ma'am. Okay, ma'am. Thank you.
I will join after our meeting.
Yeah.
Okay.
Okay, thank you.
Yeah. Thank you very much for your kind of acceptance, and you can go ahead, sir.
Thank you, ma'am.
Join later, sir.
Okay, thank you.
Thank you, Mohammed and ma'am. And now it's a time for a break. We will catch you around 11:30 a.m. again with the same link. Don't leave from this link. Suppose if you want to present your oral art poster, those who were absent yesterday, you just register your name through our WhatsApp group or by sending mail. So we will just intimate to our convener and we will give one more session for you. Thank you. Thank you so much. We will meet you again in the same link by 11:30 a.m. Indian Standard Time. Thank you so much. Now it's the time for break. To the participant shake concern up to day 2, the active participant what we have recorded, the name is Ritu Das from IIT Delhi, and she asked more than 10 questions, even yesterday session also, oral presentation today also. And after that Mr. A Dharmanandam from Vivekananda College. After that Dr. Mail Manigandan, I don't know exactly pronunciation. So we just recorded their name, and still we have one more day. So based on the third day, we will give a best interactor award to one of the participants who rose more questions in an effective manner. Thank you so much. So up to today itself, Ritu Das from IIT Delhi is in top hierarchy. Thank you.
Thank you. Thank you.
Good morning. Mohammed, are you there?
Yeah. Good morning.
Yeah, good morning. Shall we start?
Yeah, we can start. Dr. Martin Peacock is here.
Yeah,
Yeah, I will give a short introduction about him
yeah.
before starting. So, thank you, Dr. Martin Peacock, for joining us today. So,
Thank you.
So, Dr. Martin Peacock is an industrial bioelectrochemist with over 20 years of biosensor experience, having industrial roles from Abbott diabetics to GSK and solving technical challenges from continuous glucose monitoring to RNA analysis. In recent years, Martin has set up biosensor-focused companies across the globe, from Silicon Valley, California to Oslo, Norway. At Zimmer and Pico is now distilling their experience into providing a turnkey solution to accelerate collaboration from their research in the lab to product shipping from the loading bay at the factory. Zimmer and Peacock achieved this acceleration by providing a range of products and services, including sensors, electronics, apps, laboratory testing, cloud databases, IP generation, and turnkey manufacturing. Zimmer and Peacock works with clients from academia and industry with focus always set on getting to market. So, Dr. Martin Peacock, you can start with your presentation. Thank you for joining us. Hello.
Sir, kindly unmute your audio, sir. Martin, sir.
Dr. Martin, please unmute your.
Yeah, thank you very much for introducing me, and thank you for guiding me on the microphone. Hopefully, I'm coming through loud and clear. If not, somebody give me a little note in the chat, but I will carry on. So, yeah, well, thank you to the organising committee for having ZP attend this conference. I'll just give you a quick, what our intention is. I will give a sort of an introduction to Zimmer and Peacock and a quick introduction to some of our products and some of the work that we actually do at Zimmer and Peacock, and then about in half an hour's time, my colleagues will join, and we will then do some live demonstrations of our products. So I'll try and go a bit faster, just making sure that the technology is working. So in a bit, we'll be giving a live demonstration, and we'll be doing the Cyclic Voltometry of ferricyanide of capsaicin. So we'll be, I wouldn't say so much teaching cyclic voltammetry, but definitely doing some demonstrations on cyclic voltammetry. We'll also be doing some live demonstrations on amperometry, and we'll be detecting oxygen as the analytes in that lecture, or in that demonstration. And we'll also be doing a demonstration on potentiometry using a screen printed pH sensor. Just for everyone's interest, I think pH is probably the most measured chemical parameter in the world. So, pH is always kind of interesting to, let's say, measure. We will be using a couple of our products to do this work today. We'll be using something called the Anapot, which is really a sort of small size potentiostat. And we'll be using something we call our hypervalue screen printed electrodes. These hypervalue screen printed electrodes, they've been sort of 7 years in development. We use these an awful lot in our work, and then we, essentially use them with collaborators as well. If you're ever interested in Zimmer and Peacock in India, we have a very good representative here called Technando, and Technando have actually, they've been moving us onto the government e-marketplace for, so our products are also available now through there. At Zimmer and Peacock, we've got some of our engineers are attending this morning, so you'll see it in my slides. But in total, there's about 85 of us at Zimmer and Peacock. But I know that some of them are going to get up nice and early this morning and attend the conference. It's probably worth saying that I appreciate the engineers coming along this morning, because there's a really they're living in Norway, most of these guys. So I mean, it's I'm talking to you from London. It's 6 a.m. in London at the moment, and 7 a.m. in Norway. So I do appreciate the guys who are supporting us from ZP this morning. As I say, I'm going to do a 30-minute introduction. I'll do a quick introduction to ZP and myself, not too long. A quick introduction to some of our products. A quick talk on agricultural sensors. I think it's our intention this morning is to kind of give training and educational insights. But it's also interesting, it's nice to know why should any of us do all of this work. And, at Zimmer and Peacock, we do a lot of biosensing for the medical market. We're also interested in the food and water quality market, and we're also interested in the agricultural market. And then, like I say, after 30 minutes, we'll do electrochemical demonstration, and we will also then do a summary and questions. Now, if you have any questions, you can put them in the chat, etc. I mean, maybe put them in the general chat, and we'll be able to see the questions as they come in. But don't worry about asking questions. We certainly enjoy. We certainly welcome them. So, just a quick resume. As I say, my name is Martin. It's very nice to meet you all. I'm a chemist by training. I'm an electrochemist by PhD, and as mentioned, I have had industrial roles in very large companies, including GSK as a medicinal chemist, and then Abbott Diabetes as an electrochemist. I think my career has I've started off in some of the world's biggest companies. Then I went to some very small companies. Then I launched my own company. And now, I'm trying to grow my company back to be, a large company again. So I think it's useful to have had all those different experiences, both corporate and startup and starting your own businesses as well. I have founded a lot of companies, and these are ongoing, so we have companies in the USA, UK, and Norway. We have a company in France, for example. So, I'm a director of several companies that most of them are actually focused around bioscience, biosensors and electrochemistry. So if you're interested in contacting me or contacting us, you can find me on LinkedIn. That's a good place to find us. We're rather unusual at Zimmer and Peacock, though we are industrial. We do have a lot of very strong academic collaborations. We sponsor and give lectures at a university in Norway. Just out of interest, if anyone's particularly interested in joining ZP, they run an international master's program at USN. So I showed a picture earlier on of some of our engineers who originally were from India. And most of those people actually came to Zimmer and Peacock through an international master's, an Erasmus master's from a university called USN. So yeah, we've got strong ties to a university in Norway called USN. I'm a senior lecturer at Swansea University, so I'm able to give lectures to the students there. And we're also very integrated with the University of Oxford, a gentleman called Richard Compton there. And we license technology from there. So Zimmer Peacock, we were launched in 2014. Many of you who have been in electrochemistry for 20 years obviously wouldn't have heard of us, 10 years ago. So we launched in 2014. Today we're 85 employees. So in the sort of, very niche area of electrochemistry and electrochemical technologies, we're by far the fastest growing business in that area. We're ISO 13485. So it's, that means we have a certain quality to our products and our work. And it's recognized through quite stringent certification. As I say, we're at least in Norway, UK, and actually the USA. At the moment, we're sponsoring 4 PhDs. We're kind of unusual because, 85, people in total, but actually, we 5%, but per head, we actually sponsor 4 PhDs. It's quite unusual for a company of our size. If you want to know about Zimmer Peacock, we do have a strong website. I think, a lot of people do follow us on social media, and on social media, we do put out a lot of information regarding the company. We do carry a lot of biosensors. So we have one of the largest range of biosensing in the world, from sort of glucose, oxygen, lactate, hydrogen peroxide, pH, chloride, potassium, calcium, alcohol, nitrate, nitric, ammonium, uric, sodium, phosphate, sulfite, redox, ketones, And we have fructose up there, and we also have purines. This might be interesting to people who are actually sort of in their learning phase of electrochemistry. We do have something called the ZP Academy. And on the ZP Academy, you can find a couple of free courses on electrochemistry. When we first started off the business, we started off with a single office. These days, this is our R&D center. This is in Horten in Norway. This is our newest manufacturing center. This is a 4,000 square meter facility. It sits on top of a hill. It's very modern and very spacious for doing all our manufacturing in. This is a new R&D center that we've opened up in the UK. We have 2 labs here and office space. It's near the University of Warwick, in a town called Coventry. And this is a new office that we've opened up in Swansea, which is also on campus at Swansea as well. The facilities at Zimmer and Peacock are really world class. You know, we have world class laboratories. We have class 7 clean rooms. You know, we have a lot of electrochemistry equipment. You know, parallel potentiostats. You can see in some of these images, the people are wearing sort of hazard suits, you know, so we're very careful. And what we're doing is we're protecting the experiments from ourselves. You know, we do a lot of cellular and molecular biology, and we just want to keep the environment as clean as possible so that we can make sure that we get the best experiments possible. This is a picture taken at the end of 2020. It gives you about half the company, and there's a more formal image of about half the company. As I say, there's 85 of us in total. So when you add up all the people, you can see that not everyone's there. We're very lucky. I mean, if you ever visit Zimmer and Peacock, you know, we have very nice lecture theatres. And then we also have a very nice kind of culture at ZP. This is just some of the images that we took at the recent company, I would say company party, but company meeting. Also, if you're an academic or you're in academia in India, we do also get involved in people's projects. So these are some of the master's projects that we got involved with. This one's very IT related, developing apps to support biosensing. This project this one was with Yassas, this one was with Sujith, developing implantable biosensors. This project was looking at fructose, and this project was making an immunosensor for bacteria. So we do get involved in people's academic projects as well. As I say, we do have the academia. So if any of the voltammetry or amperometry or potentiometry that I will mention, if that's not clear to you, then there are a couple of these courses that are free. We also have what's called the developer zone, and we have a lot of members here. This is a free resource really for sort of academic biosensor developers. And every Thursday at 8 a.m. London time, so I think that's approximately 12:30 Indian Standard Time, we do a YouTube webinar where we answer questions from our ZP Developer Zone community around biosensing. You know, we do have a focus on electrochemistry biosensing and the commercial exploitation of biosensing as well. So to get started with Zimmer and Peacock, you know, often if people are doing, you know, sort of biosensor development, one of the first places to get started with Zimmer and Peacock is the screen printed electrode. So at ZP, we manufacture a whole range of screen printed electrodes, platinum, gold, graphene, and graphite. So our top selling screen printed electrode happens to be a graphite electrode. I'll talk about that in some detail. I think the next phase, you know, once you've got a screen printed electrodes, it is pretty important to make some, let's say, good electrical contact with that screen printed electrode. And so you need a connector, and we'll talk about that in a bit. Everything we do at Zimmer and Peacock sort of focuses around biosensing, and then those are electrochemical biosensors. And then you therefore need, in the R&D phase, you need a potentiostat. So this is our anapot potentiostat. Zimmer and Peacock is kind of unusual because if you go on our web store, you will see screen printed electrodes, you'll see connectors, you'll see the anapot, for example. This makes us really, really, really unusual. I'll ask a question which many of you might already know the answer, but the question is this simple. Who is the biggest consumer of Zimmer and Peacock products in the world? And the answer is, it's Zimmer and Peacock, which makes us really unusual. So our products are actually all used by us. And then we happen to put them onto the web store. And it's really important because these screen printed electrodes, when you look at screen printed electrodes, you know, some people complain about them. They complain about the reproducibility, the quality. You know, these are complaints. And what's happening is that the producers of these screen printed electrodes don't necessarily use them in their own products. Zimmer and Peacock use these electrodes in our own products. So it's in our absolute interest to make sure that these are absolutely the best screen printed electrodes they can be, because we need them to be. We use them in our products. Now, there's something also kind of unusual about Zimmer and Peacock as well. And that is we also have what's called a Julie, which is a cloud database. And I just realized I was going to give you a bit of a demonstration on Julie. So I'm just going to load Julie up as well. So if you're using our screen printed electrodes, you're using our connectors, and you're using our potentiostats. We also have a cloud database called Julie, where you can actually upload ZP. You can upload your electrochemical data. You can upload it there. You can store it there. You can share it there. You can analyze it there. And that's a free product. So we at Zimmer and Peacock, we use all of these things. We use our own screen printed electrodes. We use our own connectors. We use our own potentiostats. And by the way, we put all our data into a cloud system called Julie, where we store, analyze, and we can share our data. It's probably worth saying that in India, you know, all these things could be coordinated and found out about through a company called Technando. It's technando.com, and you know the team there are extremely knowledgeable on us as a business and also on our products. So what I will do now is just transition quickly. So as I say, at ZP, we do, you know, the materials that we commonly have are gold, platinum, carbon, and graphite, graphene rather. This was some data that came through yesterday from us. So this is the Cyclic Voltometry that was captured on some of what we call our hyper-value carbon electrodes. And the only reason I mention it is because if you look at screen printed electrodes, if you get something like 5 screen printed electrodes and you test them with a electrochemically active molecule, you'll find that they can be actually quite variable. But this was the data that we recorded yesterday on our sensor, and you can see that the peak position and the peak heights are really overlapping. And this is, I would challenge people to find other sources of screen printed electrodes other than ZP where you could find this kind of reproducibility and quality. And at ZP, I suppose reproducibility is everything, because we want to turn these screen printed electrodes into biosensors. If the screen printed electrodes are not reproducible, then the biosensors are not reproducible, and then it's very hard for you to make an accurate measurement upon those said screen printed upon the biosensors, because the biosensors are not reproducible. So we do put a lot of, let's say, effort into the reproducibility of screen printed electrodes. Just to talk about our connectors, we started supplying connectors as well. And, you know, this is known to everyone, but essentially we do have these connectors, and with our value and hypervalue electrodes, I suggest we have a connector type that's called the 7mm connector. The reason I bring it up is because here I have 2 cyclic voltammograms. One of them is labeled expected and the other one was actual. The actual one is somebody was using one of our screen printed electrodes and they were getting, really distorted data. But what we realized is their connectors that they were using were giving very poor electrical connection to the screen printed electrode. So as soon as they purchased a proper connector, the data just immediately transitioned to something that was a lot more beautiful. And this is quite common. You've got to be really careful, with electrochemistry that, the quality of your signal can be influenced by many things, but one of them could just be as simple as connection. So, so you can't crocodile clip or alligator clip to these kind of connectors. You do have to, to these type of electrodes, you do need a decent connector. Now we also have a set of electronics. These set of electronics will sit in the palm of your hand. They're quite small. We have the software, and we can do linear sweep voltammetry, differential pulse voltammetry, square wave voltammetry, chronopotentiometry, amperometry. So we do have all the sort of cyclic voltometry, all the kind of techniques that you would normally expect. We also have a version that does EIS, electrochemical impedance spectroscopy, as well. So this is an instrument that you'll see the guys in a few minutes. Some of my guys will log in from Norway. As I say, I'm in London at the moment, but some of the guys will log in from Norway. And when they do their demonstrations, you'll see them using this software and those potentiostats. Now, Julie is an online database for, as I say, it's really unusual. It's free to open up a Julie account. I'll give you a little demonstration in a minute. It's compatible with we use it at Zimmer and Peacock a lot. The reason that we use Julie is because, even when you're doing academic research, whether you're doing academic research or research within companies, the question you can ask yourself is, where is my data? Now, you might individually know where your data is, but if I ask you a question, where is the experiment done by your colleague on the 20th of December, 2021? You might have to go and ask the colleague where the data is. And so, at ZEP, we make sure that we actually have a database in place, which is called Julie. When you open an account on Julie, you get an individual account, and it accepts data from the ZP products. That is the Anna pots. If you have palm sense potentiostats, it accepts that data. If you have instruments called CH instruments, it accepts their data. If you have Autolab data, it accepts Autolab data. So the next thing I'll do is a quick demo. So I just want to sort of bring up my website. So I hope that you can now see my website. And what I will do is I'll just show you that under news, under news updated daily, we have importing electrochemical data into Julie. And the reason I show that is we have a couple of trial files, one from Palm Sense or the Anna Pot, one from CH Instruments, and one from Autolab. So this is data from essentially 3 different vendors. And then I would just show you this. I've logged into Julie myself this morning. So this is julie.zimmerpeacock.no. I have a bunch of reports here. I'm not going to give you let's say a sort of full demo, but I will just show you that I just downloaded some data. So I'm just going to very quickly upload the data so I can see that my downloads here. So I'll just open up the first file. So that's the file gone up to the database. I can have continuous measurements or discrete measurements. This is a cyclic voltammogram, so we consider this essentially a one-off experiment, discrete. So I just choose that. That's all good. And when I close that, then it's actually uploaded the data. So this is really, in my opinion, really useful because this is 3 different vendors who all have their own software. but actually I can now see this file, essentially in the cloud. I can analyze the data in the cloud, and I can share the data in the cloud. So what I'll do then is I'll just show you that was CH Instruments, which is a vendor of a potentiostat. This is some PalmSense data, which is, PalmSense is pretty popular. We also have the Anapot potentiostat. We're better off with the Anapot at ZP because we understand it better. But I know that that's a very popular instrument in India. And then I can see that kind of data as well is up there as well. And we can sort of turn things off or turn them back on again. And then lastly, I'll upload some Autolab data. Autolab used to be popular. I think it's being sort of superseded by things like Anapot and people like PalmSense these days, but here's some Autolab data as well. And there's the Autolab data. So the reason I was let's say showing that was I wanted to show you that at ZP we have screen printed electrodes, we have connectors, we have the potentiostats, and then we're unusual that we have we have a lot of free products and services as well. The things that would be free this morning have been the ZP Academy. You can just sign up for an account on the ZP Academy. There's a couple of courses there. If you're in academia, the developer zone is also very interesting, and it's free. And we do these webinars once a week at 8 a.m. London time. And then we also have the Julie database where you can share, analyze, and store your electrochemical data. In India, if you want to get hold of us, there's a company called, we have some very strong representation called Technando, and it's definitely worth contacting them. And they've also, been moving these products onto the e-marketplace run by the Indian government. One of the things that's really moving us at ZP is, why do we have all these products? And it's because we're really part of a sort of Internet of Things movement, let's say. A lot of people are, we're very application and app driven at ZP, but we're also driven by the idea that it's going to be a lot of sensors in a lot of applications. The nice thing about electrochemistry and electrochemical biosensors is that the technology can be very low power. You can drive potentiostats using the battery on your phone. It is low power. Electrochemistry allows you to be very miniaturized, so you can make these very mobile type applications. If you look at a glucose meter, the electronics in a glucose meter are very small, can be very disposable. So the ability of electrochemistry to be miniaturized also allows it to be part of this IoT revolution. The fact that you can, we make a potentiostat that connects to a phone via Bluetooth. So we can have connectivity. You've already seen that at ZP, we have cloud computing, we have Julie. So, the Internet of Things, is about, putting sensors in the real world and moving the data to the cloud. And, something that at ZP, our we have a small data sciences team, and some of those engineers are in India. Data science is really helping both the Internet of Things revolution, and it's also helping, this biosensor revolution. Data science allows us to kind of, filter our data, to calibrate our data, to remove artifacts from our data. So we're very appreciative of it. And we're also very appreciative of, this revolution in the availability of smart devices. This is really helping the Internet of Things revolution and, helping companies like ZP roll out our technology much faster. So I've talked about some of the R&D tools that we have at Zimmer and Peacock in terms of, screen printed electrodes, connectors, potentiostats, Julie, where we, upload, store, and share the data. That's because it's enabling us at ZP to work with our clients and work for ourselves on Internet of Things type technologies. And one example of Internet of Things technology is using sensors in agriculture. So whether you're in India, Europe, the USA, this is a common phenomenon where people or farmers are using fertilizers on the fields. So, and now in this case, I'm specifically talking about nitrate fertilizers. And these nitrate fertilizers are obviously intended to kind of put nitrates into the soil to increase the yield of the crop. And that's the intention. Now, the reality is that nobody is measuring the nitrate in the soil itself. So you put the nitrate onto the field, you hope it gets taken up by the roots and ends up, in the sort of plant matter. But in reality, it's unmeasured what's going in the soil. So it can end up actually getting washed into the water courses or seeping into the water aquifer here. Either way, the nitrate's actually ending up as a pollution source. So at ZP, what we've been working on then is a sensor system that's electrochemical. And what we were intending to do and what we've done is to put those sensors into the soil, so they're constantly measuring the nitrate in the soil, and then we're sending the data via wireless communication to people's smart devices. So if I I've introduced Zimmer and Peacock this morning and said, it's a fairly large biosensor business that sells these screen printed electrodes, the connectors, the potentiostats. We have the cloud database. The reason we have all that technology is because we're actually working on problems like this, which is, there's a real world problem. There's indiscriminate use of nitrates in farming. Nobody's really measuring it. Nobody's controlling it. And, the farmers and a group of people called agronomists need to know this data. And so we're developing a nitrate sensor to do that. Part of the mission at Zimmer and Peacock is to work with academia. So this is Professor Tony Miller. He was the gentleman who invented the nitrate sensor. And so what we've done at Zimmer and Peacock is to take his nitrate sensor and put it into a form factor that's much more robust, much more, let's say, industrialized. Now, earlier on, I showed you a screen printed electrode and said, that screen printed electrode, that's available on our web store. You can contact Technando. When you look at this module here, you're going to see exactly the same screen printed electrode in that product. So I made a very bold, very firm statement earlier. I said the biggest consumer of ZP screen printed electrodes is Zimmer and Peacock. And this is an exact example of that. There's the little ZP logo. Here's the screen printed electrode. It's in one of our products. And that's why even our screen printed electrodes are really world class, because we use them all the time. We by far are the biggest consumer of them. And our business model is unusual that we do a lot of electrochemistry in-house using these screen printed electrodes. And by the way, we also put them on the web store because we use these a lot. Now, it's one thing to do something in the lab. At Zimmer and Peacock, we like to do things in fields as well. So this is a field near Cambridge in the UK. This is me installing some of the technology in the fields. So what we're doing here is we're actually taking some of these nitrate sensors and drilling a hole into the soil and putting the sensors into the soil. And the reason we're doing this is because what it allows us to do is we have these nitrate sensors sitting in the soil. And it means that, in fact, we can see the nitrate concentration. So I can see that the nitrate concentration in this soil is about 25 or 23 ppm. Now, what happens here is the farmer adds nitrate on about, what date is that? So I'll just have a quick look. On about on the 30th of March, 2021, the farmer adds in some nitrate fertilizer. But what you'll notice is that, by the way, there's multiple sensors in the field, by the way. But what you'll notice is the nitrate goes down. But even though he's added nitrate, the nitrate goes down. And what's happened is the field is actually drying out. And so even though he's put nitrate fertilizer on the field, it isn't showing up. the reason is the field is actually drying out. Now here it actually does some rainfall, and because of the rainfall, essentially nitrate is an inorganic molecule. You know, it gets dissolved, and at which point the nitrate then shoots up. Now, because the farmer didn't understand the profile, he didn't realize that in fact he'd only just solubilized his nitrate, and in fact the nitrate now, what he did is he added another dose of nitrate here, and he didn't need to do this because in fact the nitrate was going down because the soil was dry. It rained, the nitrate came up. He's now added more nitrate, and all he's done is he's exasperated the nitrate because now the nitrate is going up even more so, and in fact it's raining quite heavily, so it's all going up. At which point he adds some more nitrate just at the same time that the rainfall has stopped. So suddenly you see this along here, we've got these blue spikes that indicate the rainfall. There is no rainfall. The ground dries up, and then it rains a bit more, and then the nitrate goes up. There's estimations that in the world, maybe 66% of the nitrates that are put onto farms are actually wasted, and this data absolutely defends that hypothesis that in fact there's a lot of wastage going on. Now, at this stage, I've got a couple of guys who might be joining us for demos. So I'm just going to Slack my guys and just see if they are here. But what our intention was to do was at 1:30, so I'm about 3 minutes over. We were intending to do some demonstrations. And what we were intending to do, we were going to give some live demonstrations of Cyclic Voltometry. We were going to give some live demonstrations on Amperometry, and then we were going to give some live demonstrations on Potentiometry. We will be using throughout this mostly our hypervalue screen printed electrodes and our anapot potentiostats. So these guys and this guy. Now, I appreciate that some of this conference is intended to kind of, educate the next generation of electrochemists. So we will be doing voltammetry. There's many types of voltammetry. Today we'll be keeping it simple and just doing cyclic voltammetry. We will also be doing some amperometry. We'll be doing that with oxygen as the analyte. We will be doing some potentiometry. The nitrate sensor that I just showed you is actually an example of potentiometry. And we won't be doing this today, but we do a lot of impedance spectroscopy at ZP. And the only reason that we're not doing impedance spectroscopy is really just time. I think we've got approximately 2 voltammetry experiments to do, 1 amperometry experiment to do, and 1 potentiometry experiment to do. So that felt like, sort of 4 experiments. It was a bit overkill to do a 5th experiment. But so we will be doing voltammetry, we'll do amperometry, we'll do potentiometry, and we won't be doing impedance spectroscopy today, though we do really quite like it at ZP. We use it a lot. So what I will do is I'll just back up slightly. So the first thing that we're doing is voltammetry. So in a minute, what will happen is I will stop sharing my screen and I'll mute myself. And then one of our guys in Norway will actually take over the screen, and we will do a voltammetry demonstration. Now, what you're going to see is something that looks a little bit like this. This is the cyclic voltometry of ferricides. Now, with voltammetry, it's not always explained to people what's actually going on. But on one axis, we essentially have current, and on the other axis, we actually have voltage. And the molecule that we'll be oxidizing and reducing today is this ferricyanide, which can be reduced to ferrocyanide. It can be reduced to and it can be reoxidized. The ferrocyanide can be reoxidized to give ferricyanide. There's a particular sort of what we call a triangular waveform behind these experiments. We often increase voltage with time, and then we bring the voltage back down to the original voltage with time as well. So it's essentially forms a triangle. We have a starting voltage, we have, let's say, finishing voltage, which is out here, and then we return to the original starting voltage. So that's the waveform behind cyclic voltammetry. If you want to dig deeper into this at another point, like I say, we do a webinar every Thursday at 8 a.m. London time, and we also have those ZP Academy courses as well. I think the guys will do it on one of our graphite screen printed electrodes, and we'll be using the Anapot to do this. They might do the experiment quite simply today, where they just put a solution essentially on the tip of the electrodes, as indicated by these kind of red squares here. So the next slide now is the demo of ferricyanide. Now what I'll do is I'll stop sharing my screen, and I think the guys in Norway will take over. Like I say, I appreciate them joining this morning. It's approximately 6:30 here in London. Norway's an hour ahead of us, so it's about 7:30 their time. So I will stop sharing, and I'll go quiet for a bit, and then we'll see if the guys kick in.
Hey, so my name is Solran, and I'm a scientist here at Zimmer and Peacock, and this is Andre Fernandez.
Hello.
As Martin said, we will demonstrate to you different ways, different measurements. And we will start with cyclic voltometry. So what we have here is a hypervalue carbon sensor. So we'll insert that into the potential.
All right. Are you sharing your screen or are you sharing the screen and video this morning? Oh yeah, I see you. Yeah, I do see you guys.
She has to be chosen as the speaker by the.
Ah, I see.
All right. By the owner of the room.
Yeah.
Okay. So the owner of the room, you might have to highlight Solran as the speaker this morning, so that she jumps up. I can manually find her by navigating. Whoever's controlling whoever's the kind of essentially the host, you might have to select Solran. But in the meantime, Solran, you carry on, and hopefully the host will essentially find you manually, make you the main presenter, and then you'll jump up. But I did see that you have your video on, and I did manually find you guys. So if you want to carry on,
right.
and hopefully that'll get fixed.
So in case you found your way to our screen, here is the hypervalue sensor inserted into the potential stat. And what we'll do next is we'll pipette 50 microliters of the ferrocyanide solution that Martin was talking about, and we will pipette that onto the electrodes so that it covers all of the electrodes. That it covers the electrodes is a bit hard to show you, as it is such a small volume, but this will suffice.
Yeah, if anyone's struggling, what I did was I clicked through all of the people in the conference, and then I double clicked on Solran and the team, and now I do have full screen on you guys, so I'm getting a good experience. But
right.
hopefully everyone else can do the same. But I do see you guys very clearly, so thank you.
Okay, so what we will do now is
I realized that Andre just turned the laptop off.
Yeah, our senior scientist just managed to turn off the computer. But that will be a quick fix.
All right. So as you do that, I can see that what you've got there is, in front of you there, I can see you've got the screen printed electrodes. So the far right, they have essentially a screen printed electrode in a connector. They've actually got it on a cable. They've also got a little stirrer in front of them. There's a black box just in front of, or between Andre and Solran. That little black box is actually the Anapot. So I was talking about it being hand-sized earlier on. And I think this is a good example that we definitely dine at our own restaurants, because we do use our own equipment, day in, day out at ZP. So you can also see that they've got these little boxes in front of them. And those boxes is because when we ship these 200 electrodes, we We ship. Yeah, that's good. So what Mott's is doing is he's just zooming in. He's just zooming in on the screen at the moment. So the guys are probably doing a first sweep because they probably started the experiment. Andre then shut the computer down, and then they've restarted it up. So yeah, Sol running. It's all looking pretty good. So maybe take us through it a bit.
So what you see here is the oxidation peak. So as Martin explains, we have a 5 millimolar concentration of ferrocyanide solution. So we're basically oxidizing to ferry and reducing back to ferro, and that's what you can see here.
Great. Can you yeah, if you run through that experiment from the start, because it was so if you do the sort of, what did you do? Did you pipette the solution onto the screen printed electrode? Is that how you did it?
Yeah. So what you see here is the potentiostat, and we inserted the hypervalue carbon sensor into the potentiostat. Then we pipetted 50 microliters of that ferrocyanide solution onto the electrode. So all the electrodes are covered, as you can see here. And then we ran the scan. So it's pretty easy measurements.
No, I appreciate that. I think that's actually a really important point, to be honest with you, because once upon a time, doing electrochemical experiments was, there was a lot of trailing cables. You were doing a lot of crocodile clips, and these days you can sort of plug these electrodes into the front of these instruments. Pipette on, like Solron said, 50 microliters of solution. And then you can run this kind of software. An experiment like that might take 30 seconds, depending on scan rate and on the voltage, but it's very, let's say, quick to do. And it's a very clean kind of experiment as well, that they needed to do that experiment, a laptop, one screen printed electrodes, and the particular potentiostat. Now, what I'm going to do is I'm going to share my screen now, because the guys are going to prepare for another experiment. So hopefully now people will start seeing my screen. So my screen should now. So if you're having problems seeing my screen, navigate around a little bit, but I'm sharing my screen, and it should say to you, demo ferrocyanide voltammetry. What I'm going to do is we're going to do a second experiment. So what's going to happen in a bit is I will stop sharing my screen. You might have to navigate around and refine Solrun, because the guys are going to do another experiment. And what they're going to do is they're going to do an experiment using a molecule called capsaicin. Capsaicin is the molecule that you get in chili products. So we have a lot of customers in India using a product from Zimmer and Peacock called FoodSense. FoodSense has a chili sensor in it. This is an IP protected technology that we licensed from the University of Oxford, and it uses some electrochemical techniques. Now, what you're seeing at the moment is a animation of the cyclic voltometry of capsaicin. That first peak that you see is due to an oxidation of capsaicin, and then you'll see in a minute what we call a reduction peak. That's the reduction of a derivative of the molecule called capsaicin. And then on the second scan, you'll see a new peak. Now, I'll explain where all that's coming from. Peak number 1 is due to the oxidation of capsaicin. Now, what we form is it's really a cation. It's a positively charged organic molecule. What happens is that cation hydrolyzes. It reacts with water and actually forms a new molecule. So what happens is capsaicin has what we call a sort of methoxy group. When we oxidize it, we call that an E, it's an electrochemical step. It then has a C step, which is a chemical step. So we have electrochemistry and chemistry happening in the first wave. Now, when we get to the second wave, we're actually now doing the reduction of this quinone to a quinol. This is a new molecule that we formed during the experiment, and this quinol sticks to the carbon surface, and then we get a new peak. We get a new peak because, in fact, the quinol which is new, we formed it during the experiment, reoxidizes to a quinone. And so capsaicin has a unusual cyclic voltammogram. Ferricyanide was quite simple. We had oxidation, we had a reduction, it was quite repeatable. With capsaicin, the second scan is very different from the first scan. We actually have a new peak in there. And it's because during the first scan, we do the oxidation of capsaicin, it reacts with water, we get a new molecule. The new molecule is reoxidized in the second scan. So that's why capsaicin is quite, let's say, unusual. So whenever you see this kind of demo, that means then that what I will do is I'll stop sharing. Once I stop sharing, then you'll have to navigate back to the video and try and find Sol running among all the list of attendees and click on her screen, and then that should become larger again. So I'll stop sharing. In fact, I can see Sol run quite readily because I've left you highlighted from the last time. So I see you guys. Yeah, go ahead, Sol. Are you on mute or can I hear you?
No, we're on mute. So what we will do now is, as Martin said, we'll run another cyclic voltometry, this time with a solution containing capsaicin. First, we're going to run a solution with Tabasco, a fairly strong chili, and we mixed it with our chili powder.
Can I just ask if you're not a speaker at the moment, can you mute your microphone so we get a bit of pick up on people's microphones? Thank you. All right, carry on, Solron.
All right, so what we will do, we'll do the same as we did before. We will pipette 50 microliters of the solution. We cheated, so we already mixed the solution before we got here. But yeah, as I said, it's a mixture of a buffer and the Tabasco sauce, so that we have an electrolyte in the solution. And so I covered all the electrodes with the solution now. And what I'll do, I'll hit run, and it'll start scanning. And as Martin said, we will, on the first scan, we'll run 2 scans. On the first scan, we will see a oxidation peak, and then it is going back down in potential, and we'll have a reduction peak. As you can see, this scan this time is going a bit slower than last time, and that's because we have decreased the scan rates. So now it's going for the second scan, and there you see we get an additional peak, additional oxidation peak. And now the oxidation peak for the capsaicin has reduced, as we have less capsaicin in the solution after the first oxidation and the second oxidation that happened here. To follow up on this, we will now try a weaker chili solution. So we will change the solution for a weaker one. So what I need to do is to swap the sensor, because it's a one-time use sensor. At least this one is, and we will insert the sensor, and now we will get our pipettes. We will again pipette 50 microliters onto the electrodes of the sensor. And now that that's ready, we will run the scan one more time. And you see the oxidation peak is coming over there. And if you compare it to the other, to the scan that we did before for the Tabasco sauce, you'll see that the oxidation peak should be lower than it was for Tabasco. And so the red one is the Tabasco, and it has an oxidation peak actually exceeding the screen of the computer right now. Here. So the red one is the Tabasco, and the yellow one now is the Sambal Ulek. Don't know how to pronounce that, unfortunately, but as you can see, the oxidation peak is way lower, which indicates that we have less capsaicin in the solution. And capsaicin is related to the Scoville heat units, so hence it indicates the strength of the chili sauce, which we just demonstrated now with these two peaks belonging to Tabasco and these two peaks down here belonging to the Sambal Ulek. Yeah.
Brilliant. Well, thank you, Solran. I will share screen again, which I'm now doing. And we kind of gone quite quickly into voltammetry, but as Solran indicated, the peak heights that you see are indicative of the concentration of the analyte of interest. So when she used a strong concentration of capsaicin, the peaks were higher. When they used a weaker chili sauce, the peaks were actually lower. So, you know, when you talk to an electrochemist, they'll tell you that the scan rate dictates the height of these peaks, but also the concentration dictates the heights of these peaks as well. So the next thing we're going to go on to is amperometry. Now, in amperometry, we said with cyclic voltometry, we said that we're using a square wave voltammogram. We start at 1 voltage, we scan to another voltage, we scan back to the original voltage. No, not square wave, triangular wave. So in cyclic voltammetry, we were using a triangular wave. We went from 1 voltage up to another voltage and then back down again in a triangle. Amperometry is much simpler. We just apply a voltage and we keep it constant. Now, so for example, you know, if you're making a glucose sensor, a lot of those glucose sensors, at least what's called CGM, continuous glucose monitoring, the generation 1 continuous glucose monitoring sensors often work at around about 650 millivolts. If the solution is not stirred or there's no membrane on the sensor, when you look at amperometric experiments, you can often have this kind of high signal at the beginning of the experiment and it decays with time. And this is really because of diffusion, that what happens is you're doing electrochemistry and you're essentially exhausting the molecule. We're depleting the molecule. And so the signal falls as a function of time. If you see that kind of response, then we often classify that as a Cottrell response. Now we're going to do a practical demonstration on amperometry. And what's going to happen is in amperometry, you follow current as a function of time, and the current that we see is proportional to concentration. Now, amperometry as a technique has been around for a very long time. I mean, there's something out there called the Clark electrode, invented by a guy from the USA in about 1956 called Leyland Clark. And he invented the oxygen sensor. A couple of years later, he really invented the glucose sensor. But the oxygen sensor that he invented is really an amperometric sensor. So the demo that we'll be doing in a bit is we'll be taking some of our platinum electrodes, and there'll be 2 phases to the experiment. There'll be a phase where we're doing the reduction of oxygen. So we'll have a current. The current will have a negative signal, but that's just indicating the flow of electrons because we're doing a reduction. And then when the guys add in what's called an oxygen scavenger, the signal will go much closer to 0, so it'll suddenly transition. So this is sort of the profile that you'll see in a bit. And it's because they're applying a negative voltage, they're reducing oxygen. When they add in what's called an oxygen scavenger, so in the first part of the experiment, you'll see the reduction of oxygen to probably water. Then they'll do a oxygen scavenger, and which point they'll deplete the oxygen, and then the signal will go close to 0. So as I say, whenever you see this kind of demo slide, then I will mute, stop sharing, and then it will change over to the guys in the laboratory.
Hello, everyone. So I'm just following up on the demos here after my colleague, Solon. So what we are going to demonstrate now, as Martin said, is the oxygen sensor. So we're going to use, we're going to apply a negative potential of minus 625 millivolts, which will allow us to reduce the oxygen on our electrodes. So we are going to use a screen printed electrode, the ZP screen printed electrode. In this case, I'm actually going to dip the electrode in a solution. That's why you are looking at this setup. So the electrode is here. It's connecting to the anapod via these crocodile clips and this wire. And what we are going to do is, so now I will immerse the sensor in the solution. This is just a PBS solution. And once I immerse it in the solution, so you can see that this is fully immersed, the electrodes are fully immersed, and then what I'm going to do is I'm going to add a little bit of sodium sulfide in order to eliminate the oxygen in the solution. But before that, we're going to first acquire a baseline, and once we wait for about 40 seconds, 50 seconds, and once that baseline is acquired, then I will add an oxygen scavenger to the solution and see the sensor's response. So this is a typical amperometric curve. So you see first there is an increase. It starts at a higher current, then it gradually goes towards a baseline. This is like a charge effect at the interface between the electrodes and the solution. And so I presume, so this has been pre-wetted before this electrode. I presume we have quite a good stable line. What I'm going to do is this is not very scientific. I'm just going to add this oxygen scavenger to the solution. And as you can see, once my colleague Solon zooms in, you'll see a step. So without oxygen and with oxygen. So I believe this is the best demo I can make at this moment. And so if there is any way of me putting back a new solution, putting back as the oxygen comes into the solution again, then you would see again a decrease in the current observed. So thank you very much for watching.
All right, well, thank you very much, Andre. So what I'm going to now do is I'm going to share my screen again, and we will go on with, so I think if I was to sort of recap a little bit this morning, so, we introduced our hypervalue electrodes, which the guys actually used twice. So I said, here's some hypervalue electrodes. They used those hypervalue electrodes in the first CV that they did on sort of ferricyanide. They then reused hypervalue electrodes, again using the anapod as well, in order to do the CV of capsaicin. And in that experiment, they actually did essentially two experiments, because they did one with a lot of capsaicin, one with less capsaicin, and you saw the difference in the magnitude of the signals. And then Andre just did a quick experiment on an oxygen solution. So we were looking at the reduction of oxygen, and then he added some powder, which is really an oxygen scavenger, into the solution. And the question just came through and said, what oxygen scavenger have you used? And it's sodium sulfite. Sodium sulfite reacts with oxygen to give you sodium sulfate. And in doing that reaction, essentially the oxygen disappeared. And Andre said, well, I was using a voltage of minus 625 millivolts, which was good for the reduction of oxygen. But then the signal went close to zero because there's no more oxygen. And then what Andre was saying is, I can't reverse that. He can, if he leaves the solution standing long enough, then oxygen will come back in from the atmosphere, and the signal will have essentially come back in again. So we've done 3 experiments this morning. Now I'm going to transition to potentiometric sensors. So if you're not familiar with potentiometric sensors, potentiometry, is just a fancier way of saying the measurement of voltage. And you are familiar with potentiometric sensors because, you know, every pH sensor that you use to make up buffers and solutions in the laboratory, you know, these pH probes, as we call them, are really just a form of potentiometric sensor. If you were to pull apart a pH probe, you know, there's really two electrodes in there. There's often these days what we call a silver chloride reference electrode, and it's conceptually quite unusual, but the glass itself, the outer glass, is actually a pH sensitive glass, and that's actually a working electrode. The glass itself is an electrode. So if you pull apart some of these pH probes, which I'm not suggesting you do, but if you look through some of the ones that are more transparent, you can sort of see a wire inside them, and that wire is often like a silver wire, and it's part of the silver chloride reference electrode. So you are familiar with potentiometric sensors. You probably, especially the chemists and biologists, you use them, you know, every day. There is a I'm not going to derive the Nernst equation. I only put this slide up really for, you know, some of our colleagues here today will be professors, some of our colleagues here today will be postdocs, some of our colleagues here today will be doing their PhDs, and some of them will be undergraduates. So the reason I bring this up is just to say to you really that the voltage in a potentiometric sensor is proportional to the concentration of the analyte. So if we have a pH electrode, then the voltage is proportional to pH. pH sensors and potentiometric sensors. A pH sensor is really a category of electrodes called ion selective electrodes. So the ion in the case of pH sensors is protons. We earlier on did a talk about nitrate sensors, and there the sensor was an ion selective electrode, but it was specific to nitrate. With these ion selective electrodes, I mean, at Zimmer Peacock, we manufacture quite a lot of ion selective electrodes. We have the pH ion selective electrode, which you'll see in a bit. We have the nitrate ion selective electrodes, which is a patent protected technology that we licensed in. We have the potassium ion selective electrode. We have the sodium ion selective electrode. We have the calcium ion selective electrode. Now, and all of them have essentially an output signal voltage, which is proportional to the analyte of interest. So what if you ever make an ion selective electrode, or you use one of our ion selective electrodes, or you use one of our screen printed electrodes to make an ion selective electrode, there's really two sides to it. You need a reference electrode. Here I've labeled this up AgCl. So that just stands for silver chloride. And then the other electrode, which we call the working electrode, needs to be which is ion selective. And that ion selectivity, we often use what's called an ionophore, something that likes a particular ion. And we measure the voltage between them. I feel like ion selective electrodes and potentiometric experiments, if any of you are electronic engineers, it's by far the simplest circuit of, it's one of the simplest circuits that you can design. So the one thing that's nice about potentiometric measurements is if you're trying to make low-cost electronics, it's fairly straightforward. So in practical ways, I've talked about, there's a silver chloride and there's an ionophore or a working electrode. And so we often functionalize the black line. You'll notice this is the same electrode that we've been using throughout. I talked about the ZP hypervalue carbon electrode. We've been using the same one throughout, except in the experiment that Andre and Solron are about to do, they'll be using a working electrode that is pH sensitive. And then they will be using another of the electrodes on board, which is silver chloride, as their reference electrodes. And the instrument, the nice thing about these modern instruments is they will just change the mode of measurement from it's the mode. They will change the mode of operation from being amperometric to potentiometric, and the software will just do the switching for them. So as I say, every time you see the demo slide like this, then you know that we're going to transition into another demo. So I will stop sharing. I will go on mute.
Hello.
Off you go.
Hello again. So in this instance, like Martin said, we are going to test a pH sensor, one of ZP pH sensors. So in this case, the ZP pH sensor is, it's hard for you to see, but it's connected to a connector that is connected to the crocodile clips that belong to the cable that goes to the anapod. I moved the screen. And yeah, sorry, I do. And so what's going to happen is I'm going to dip this in different pH solutions, this sensor that you see here, in different pH solutions, and we are going to run an open circuit potential, so potentiometric measurement. In this case, an open circuit potential is just measuring the potential without applying any energy, just measuring the potential between the working and the reference electrodes. So those are the only two electrodes that you need to connect on the anapod side. So I'm going to start with a low pH, and I'm going to just dip it in the solution. And as Solon is going to show now on her screen, that should be translating onto a baseline.
Click the auto scan.
So I'm going to wait a little bit for this baseline to occur. Now I'm at pH 5, and now I'm going to move towards a slightly basic solution. I first will just dip it quickly in the water just to clean the electrode. And now as I change it, so there was no change here. Sorry for this. It might be that yeah, there you go. There's a slight change there. You have to zoom more. So now we are a more basic solution, and what's going to happen now? I'm going to move it. This is now actually pH 9. I'm going to wait until 80 seconds. And then I will move it to pH 7 and then back to pH 5. So just bear with me until 80 seconds here. Here we go. I'm going to now move it. And now so it will take some time to move towards a slightly more acidic solution. So there you go. So now I'm at pH 5 again, and I will move down again to pH 9. Just I'm doing bigger steps here, so it's easier for you to see it on the screen. There you go. So I'm move to pH 9 again. So that's it. This is, again, like Martin said, this is like a potentiometric measurement. So we have, it's an ISE sensor in this case. So we have an electrode that's sensitive to in this case, to the protons. And as the protons diffuse towards the electrode, then the potential, the open circuit potential will change. And that's how we make the measurement. So
all right, well, thank you very much. What I will do then is I will share my screen again. And so far this morning, we've introduced Zimmer and Peacock. We said that that we make a lot of screen printed electrodes, which is and we also make the potentiostats, and we make the connectors, and we have the Julie database. And so if I just think about what we've run through, is we've introduced those technologies. We've we've actually talked about the motivation for all of this kind of work, which is really because, we think that electrochemistry and electrochemical biosensors can really be part of, there's essentially a revolution going on with the Internet of Things, having sensors in the environment. And therefore we transitioned to that nitrate rod, which has been a significant program for us, and a significant product. And then from there, we've now transitioned into these kind of, demonstrations of technology. And so we did 2 CV experiments, 2 cyclic voltometry experiments, a simple one with ferricyanide, you saw was quite simple. Then capsaicin, which is kind of interesting because capsaicin, the first scan was different from the second scan. And we explained that, during the first scan, we had a chemical reaction going on. And actually, so it sort of, on the second scan, we saw the product of that first scan. And then we went to amperometry, and, it was nice. Actually, that reminds me, we did get a question during the amperometry experiment. It came through on the chat. So hopefully we are picking up. If you've got any questions, feel free to throw them into the chat. So we've had essentially sort of 2 questions so far this morning. Do we ship to Pakistan, which we are happy to do? It's very easy in India because we have Technando. They really help us with the importation paperwork. Pakistan, we might need a reseller in that country. That was one of the questions. And then the technical question that came through was, how did we scavenge the oxygen? We used sodium sulfite, which reacts with oxygen to form sodium sulfate. And that's why when Andre did the experiment, we went from a negative current to something that was much more closer to 0. And then finally, we just did a pH experiment. As Andre says, I was calling it potentiometric, but in the software, you're looking for a something called OCP, open circuit potential, which really just means measuring the voltage at very high impedance. And Andre, he was changing the pH, and as he changed the pH, the voltage was moving accordingly. So thank you to Andre and Solron for that. I always think it's good. Thank you, because it's not easy doing live demonstrations. So if you do 4 experiments live, you stand 4 chances of it going wrong. It's called science. So to get 4 out of 4, well done, guys. Not easy. So we're coming to the end now. So far, ZP has talked to you almost continuously for getting up close to an hour and a half now. As you can see, I need a cup of tea. So summary-wise, let's start summarizing where we're at now. Like I say, happy to take questions. There's not too many questions in the chat box at the moment, but we're happy to take them. So we came here this morning to give an introduction to our company and to give you, some perspective on, where on electrochemistry, and then to formally introduce some experiments, and you've seen sort of 4 experiments this morning. To get started with Zimmer and Peacock, you do need screen printed electrodes. I think we make one of the highest quality, lowest cost screen printed electrodes around by a long way. You do need connectors. We do have a series of very nice connectors. You do need a potentiostat. And once you've got those 3 things from ZP, you can then really unlock this value of Julie, which is, and as Andre is showing on his screen, he's holding up the Anna pot at the moment. And it is a very small, little potentiostat, very powerful. And the power of that really is because the science itself is such a powerful subject. So once you've got a screen printed electrode connectors and a potentiostat, then you can actually upload your data to the Julie cloud, which means you'll always know where your data is. You can access it off your phone. You can share it with a principal investigator, or a principal investigator can share it with students quite readily as well. If you need technical questions regarding this, then we also have Technando in India that's able to kind of answer and coordinate those kind of questions. So I think with that, from ZP now, it's really a sort of thank you and questions and answers. We don't have any more, let's say, demos and slides, but we are happy to take any questions. If people want to ask them through the chat, or there's people want to ask us a question directly, I'll let the chair sort of determine how that really happens. But otherwise, I think from us, that's the end of our formal presentations. But we are appreciative of being invited this morning. And yeah, thank you very much.
Yeah, thank you, sir. Somebody has posted question in the chat box itself. Hopefully you can see also. If these services are available in Pakistan?
Yeah, so we do. They would be available in Pakistan. The reason I'm slightly hesitant is sometimes, importation, exportation in different countries can be quite tricky. We will sell them in Pakistan, or we do sell them in Pakistan. I don't mind if the quick answer is yes. We don't have a reseller in Pakistan. So if people know of resellers, resellers effectively a company in the country that understands, the importation exports laws, but we will, we're happy to ship them to Pakistan. We might need a partner on the ground who understands the logistics of the tariffs, etc. So yes is the answer. We might need some help from a company within the country.
Thank you. Next question is from Ritu Das, IIT Delhi. What oxygen scavenger have you used?
Yeah, so the oxygen scavenger that we've used is when Andre was doing the experiment, he poured in a little bit of powder, and the powder was a molecule called sodium sulfite. I'm still sharing my screen, so I'll show the reaction. So on my screen here at the moment, I'm showing a molecule. It's called sodium sulfite, Na2SO3, and it reacts with oxygen. And in doing that, it forms sodium sulfate. But it essentially scavenges, steals, reacts, whatever you want to call it, all the oxygen. And then the signal dropped close to zero. So the quick answer to that question is it's sodium sulfite.
Yeah, thank you, sir. And one more question from Dharmanandam, Vivekananda College. Why did you choose a non-ferrous oxygen scavenger?
Yeah, it's interesting actually, because I can see here that they've written ferrous carbonate is typically used as an oxygen scavenger. To be honest with you, I didn't know that, so we might give it a go. It might be less, if it's less toxic or just as good, then we would maybe use that instead. So I can see why the ferrous carbonate could become ferric carbonate. So I could see why that works. So the quick answer is, the nice thing about doing lectures and presentations like this is, I think on the call today, I saw there was like 100 attendees. That gives me 100 opportunities to learn something. So I just learned something is the quick answer. So good idea. Thank you for the suggestion. It's probably less toxic, that molecule.
Thank you. Participant can ask question. Either you can post in chat box also. Our Martin is happy to answer.
Whilst people think of the question, Andre, take a note of that, ferrous carbonate.
Yeah. Mohammed Aftab, are you there?
Yes. Hello. Yes.
Yeah. Shall we conclude, or?
Yeah, we can conclude now. I think there is no more question from the audience.
Yeah. Okay.
Thank you very much.
Yeah, sir. So ETARTS 2022 is feeling cherished to join with you guys with an excellent virtual live stream on various electrochemical techniques. On behalf, I would like to thank you from the IHE, Professor Martin Peacock, and sorry guys, I don't know your name, from ZP Norway, I think Soren and somebody. Without your, thank you so much. And without your support, we can't, for this, Mohammed Aftaf, for approaching us and accepting the demo on various aspects like pH, nitrate, and so many terms associated with electrochemical techniques. So once again, on behalf of ETARTS 2022, we are very happy to acknowledge to you guys, and our convener personally felt happy. Unfortunately, she is in another meeting with the official related things, and she would like to continue our collaboration in future also. We have planned to conduct one workshop in future, and we will come with you later. So with this, I would like to thank once again Professor Martin Peacock, the team member ZP Norway, and Mohammed Aftab from Technanto. Thank you guys. Thank you so much.
Well, thank you very much for having us, and thank you to Andre and Solron, who were in front of the camera this morning, and for Motz, who was behind the camera. We wish you a good conference. I'm looking forward to a strong cup of coffee this morning, and I'm going to have my breakfast now. But thank you very much to the organizing committee and to Mohammed Aftab for helping organize us to be here this morning. And it's our pleasure to be here. So thank you very much, sir.
Yeah, thank you. Mohammed, thank you so much.
Thank you very much.
Yeah, okay. Now it's announcement to the participant. Yeah, thank you. Thank you, Zoran, and I don't know about your name. Anyway, thank you so much. A kind attention to the participant. Now it's time for lunch. We will meet you again in the same link by after lunch around 2 p.m. And we have two invited lectures. One lecture from Dr. V. Murugan, CSIR Secretary, Karaikudi, Tamil Nadu, India. And the last lecture will be handed over by Professor Mamas. So we have two wonderful lecture sessions. Don't miss it. With this, I conclude this morning session. So now it's a time for lunch break. We will meet you again. Thank you. Thank you so much.
More
Hello.